They both were the founders of swarm learning as a technique. So they use this in just predicting a lot of diseases. But one of the drawback of the study that they did is they didn't use it on any image-based analysis. So it was all text or tabular information for prediction of COVID-19, tuberculosis, or any other cases or diseases. And as I already told my supervisor, his first Nature paper in 2016, in this paper, he showed that deep learning could directly predict mutations. So directly from the whole slide images, you could predict mutations in the Nature paper. So what idea we had is to combine both these studies, to use swarm learning as a technique and show that deep learning can predict mutation.
Learn about the newest digital pathology trends in science and industry, meet the most interesting people in the niche, and gain insights relevant to your own projects. Here is where pathology meets computer science. You are listening to the Digital Pathology Podcast with your host, Dr. Alexandra Zhurov.
Welcome, my Digital Pathology Trailblazers. Today, my guest is Oliver Saldana. And Oliver is the first author of this Nature Medicine paper published in 2022, and he's an author of many other papers. And this particular one, Swarm Learning for Decentralized Artificial Intelligence in Cancer Histopathology, is a novel way of doing deep learning for histopathology. And we interacted on LinkedIn, and Oliver told me about this research, and I was so interested that I actually did a YouTube video about this paper, Oliver. So I'm kind of talking about this paper. But first of all, if you're watching on YouTube, you're going to see me in a very fancy jacket. And I was motivated to put this red fancy jacket on because Oliver was so fancy when he came to the podcast. So I had to take off my hoodie and match the very professional look of my guest. Welcome to the podcast, Oliver. How are you today?
I am great. Thank you. Thank you so much. I really love your energy, the way you interact and the way you introduce me. It's wonderful. Thank you so much for this wonderful opportunity. So telling a little bit about myself, I am Oliver Saldana. I come from Mangalore. This is a coastal town in India. So I did my electrical engineering in Mangalore itself. And then I came for my master's in smart system here to Germany. So as soon as I finished my master's, I always wanted to do my PhD. And for PhD, I enrolled into RWTH, and there I was introduced to histopathology. So my supervisor was Professor Dr. Jakob Nicolas Kather. So he introduced me to this wonderful field. So since then, from 2020, I have been working with histopathology, and then I started my journey with decentralized AI.
Yeah, so Professor Kather, I never met him personally, but since I entered the digital pathology space, he was already active there. And that was in 2016 when I entered. So he has been doing this for a long time. So yeah, Oliver, please brag about your group, brag about your paper, because I'm not doing you justice by just saying, Oliver, he's the author of this and that paper. If people didn't read this paper, it's Nature papers. So that is pretty high impact factor. And your most important paper, as we were interacting, is the Swarm Learning for Decentralized Artificial Intelligence in Cancer Histopathology. And before we dive into what swarm exactly means, can you tell me about the concept of decentralized AI and why it matters?
Yes, definitely. I would like to give a small introduction on decentralized learning. So before we go into decentralized learning, it is important to know what is local learning or centralized learning, right? Because then I can give a better,
exactly, all the different concepts that we need to know before we can appreciate how novel your work is actually in the histopathology space.
Yes. So as I already told, local learning is something where you have one center with maybe 100 patients. So they want to train a model locally. So they have a physical system in which they put all the data and then they train a model. So this is called as local training, or somehow a training in a specific center. So if you have 3 centers, then how would you do training? So beforehand or previously, this training has been by putting all the data from 3 different centers into a central location. This is called as centralized learning, where you have one single center which is having the capacity to train a model for all the infrastructure necessary, as well as compute power, as well as the storage for the whole slide images. So this center trains one single model, and this is called as centralized learning. So somehow the reason and drawback in this is that you have to transfer data from one center to another. So there's a lot of duplicacy in data, as well as there will be a lot of issue when you have to share patient data, right? So that's why there is something new in the field, which is also called as distributed learning, where the data never leaves the center. Every center has its own data, but only the learning parameters are exchanged or learned or shared between different centers to train a single model. So here also you're training a single model, but actually by not sharing the data. So now comes the very interesting point, that is decentralized learning. So the technique which I already explained in this, all the learning parameters go to a central coordinator that is always to one single center or one single point. But in decentralized learning, what happens is you don't know which is the centralized coordinator. That's the whole beauty of decentralized learning. By actually sharing the learning, training a model by actually not knowing who is the central coordinator. So this is basically what decentralized learning means: training one single model without actually sharing the data, only sharing the insight, but still not to a central coordinator. So the central coordinators keeps rotating. So it can be one center on each run. It can be multiple centers on different runs. But this is what is decentralized learning.
Okay, let's take a step back for just for me to understand. So centralized is you put all the data together, and you like have one model that has different learning parameters, and those learning parameters would be weights, biases, and all the other things that are in this model that makes it act in a certain way on one batch of images. And the images were put together. So like they were put in one central library. And okay, that's one thing. And this is the thing that is still very prevalent. This, is part of different initiatives, and we're going to touch on those initiatives. One of the pretty famous ones in Europe is Big Picture. But okay, this is the way people have been doing this. Then you say there is a different way where you have one central model, and do you have then one other model that goes between centers, or each center has their own model and then they report to the central model?
Yes. So the model architecture remains standard or constant between all the centers. Only what goes forward and back is the weights or the learning of the model. So the model architecture is constant.
Let's say we have 5 centers, or no, let's make it easy. We have 3. We have one model in one center, another model in another center, and another model in another center. And center is, let's say, clinic, hospital, whatever, right? And then the information from those models that were learned on those local things, weights and biases, go to the central model. And the central model, but you say this is not good enough. We don't like that.
Yes, exactly.
So you don't want to have a central model that knows everything. You want them to like exchange. How does that work?
Yes, that's where the beauty of swarm learning comes in. So here what happens is, here in the previous technique where we were speaking, there's always one leader, that is one center, which is always aggregating the weights and sending it back. So weights are somehow numbers, which is the learning parameters from each center. So always there is one single center which aggregates it and sends it back after certain batches or after certain updates. So in swarm learning, what happens is this central coordinator is not fixed. So as you told in the example of 3, so in the first run, maybe one of the 3 is elected as a leader using blockchain. And somehow, since it is using blockchain,
as well.
Yes, since it is using blockchain, it is completely decentralized and no one has the control or authority to elect this leader. So this is completely random, and who elects the leader is somehow not hard-coded and it is not fixed. That's why it is using a technique where at each different sync, the leader keeps changing. That's why there's not a central coordinator. Why? Because one of the center might stop, one of the center may not have network, or one of the center might drop out of training. So the training
Mm-hmm.
should not stop. That is one of the very important reason to have not have one single coordinator, but everyone is a coordinator who's contributing to the model.
So you basically remove the bottleneck of one instance controlling this. And okay, so if we let's take it at scale. If instead of 3 we have 100, and across the globe, there is no way that everybody is going to be online at the same time. And because we have so much data, we cannot lose time for training. So you want this to continue.
Yes.
And if it wasn't complex enough, it includes blockchain. Let's talk about that. So
Yes.
blockchain, my understanding of blockchain is, layman understanding of the blockchain financial transactions, where similar to what you're saying, there's no like one central bank. It's the information embedded in this blockchain. But please give me a better perspective from a blockchain user for histopathology, which I think is also super novel concept. I don't think it's like the only, it's not the only application in healthcare, but definitely very novel in histopathology.
Yes, definitely. It's not the only application, but it's very new. So I'll give a small instance. Like generally, when you train a model, you have something called as an API. API is like PyTorch, Keras, or like just the framework in which you train a model. And then you have the data. So there is somehow a gap between an API and the data. And in between this, you have something called as a control layer. So where the blockchain comes into picture is in this layer. So this layer somehow has to have information about the parameters, about the epoch, about all the necessary information that it needs to contain. So somehow what blockchain does here is takes all this information and provides it to the API and then the data. So somehow it is like an intermediate layer, which is like a smart contract. So somehow if you have 100 centers, so you need to know which centers need to have the common parameters like the epoch, the stopping criterion, the starting criterion, and so on and so forth. So somehow it is very important for all the centers to know this common ground. So this is where the blockchain comes into picture. It is not having the weights and biases that are shared. It is just having the smart contract. That is this information, basic minimum information necessary for training. So what blockchain does is transmits this information to all the partners and establishes a secure establishment and elects a leader who does the training for a particular batch. So in the next batch, there's a new leader who is elected, and then the training continues till the stopping criteria.
So question, like if this is that those leaders are randomly assigned, is it that at the end, all of these models will have the same information?
Exactly. So what happens is this leader will aggregate all the weights and then transmit it back. So at the end of the training, what we expect is all the 100 centers or all the 200 centers to have the same weights and biases. That is the model parameters. And then this model has to remain constant over the whole consortium or the whole training platform. So somehow when you validate this model, it should perform equally to a new data set which you want to validate it on.
And how is this arranged that, okay, you will not have the same type of data in all centers? Does it like take all the information, how the slides are made, the shade of hematoxylin and eosin, and all the other, parameters that we worry about when we want to have a robust, generalizable model? So it basically like takes these pieces of information from every partner and then adds it in the leader, and then leader brings it to wherever. I hope I'm not confusing my listeners even more. I'm like coming with the attitude. I understand it after the end of this episode, they will understand as well. But yeah, I hope the question is okay.
Yes, the question is good. So I will explain it in a little bit more broader perspective.
Yes.
So somehow there are two general steps in training a model. So when we wanted to predict something like a mutation. So
Mm-hmm.
there are two general aspects. One is pre-processing the whole slide images. The second part goes to the training. So somehow what swarm learning is involved in is only the training aspect of it.
Okay.
So it doesn't do anything on the pre-processing side of the model. So somehow,
What would be the steps on the pre-processing
yes,
side?
on the pre-processing, as you know, histopathology slides are very big. So we need to do the tessellation, the normalization, so that all the histology tiles and the slides look in a similar way. And then maybe there could be some feature extraction with the new SSL methods like transformer-based feature extractors. So this is all coming in the pre-processing aspect. So you go from whole slide image till the features, everything locally. So this is never a part of swarm learning. So going from features to prediction is
Mm-hmm.
the swarm learning aspect. So giving the
Okay.
feature to the model and getting a prediction out of it is all where swarm learning comes into picture, and training the model and making it better. So somehow generalizability, different whole slide images, what are the staining. So all this is handled during the pre-processing side
But locally.
locally.
So we only have a certain spectrum that is being normalized, right? And then in the second center is a different spectrum that is being normalized. Let's
Yes.
say the first centrum has kind of darker H&E,
Mhm.
and it's normalized to that.
Mhm.
Then the other one has a lighter, the other one has thicker slides. So we still have like some kind of batch effects that can be present in the pre-processing, right?
Yes, definitely. So
Does it
there are two
matter?
ways. Yeah, there are two ways to approach this. One is you can normalize it to a standard image, that is an
Mm-hmm.
image constant over all the centers, and then everything is normalized according to this image. But there is another approach by just having this batch effect and giving it to a single model. Somehow it is good for the model to have this variability, not having same kind of images, but having, why? Because you never know what is going to be thrown into the model, right? So for a
Mm-hmm.
prediction, it can be from any center that we are not aware of. So somehow giving a little bit of variability to the deep learning model is always good for it to assess and to analyze different kinds of staining or different kinds of, like, brighter shades or lower shades. So somehow this is very good for the deep learning model to have a little bit of variation. But I wouldn't say it would perform very, very good, but somehow the model would be robust and not biased to one center. Because if it was a
Mm-hmm.
local model, then it would be biased just to that kind of features. But since it is having three centers with three kinds of color shades, so I think the model is somehow less biased to one particular center.
So this is kind of like in line when we have aggregated way of training to just have different appearances, different types of slides, right?
Yeah.
Okay, so here non-inferiority. But taking one step back, what is swarm learning? Like in the general picture, who invented it? It's not the first application in healthcare. Where was it used first? And tell us a little bit about this method as such, and then like how did you come up with the idea to use it for images?
So this is a very interesting question, and then I have a nice story for this. So
Oh yes.
yes, so it was not invented. Swarm learning was not invented by our group. It was by Warren Hadstall and then the team from HP. So this was a small group in Bonn,
From
and then
Hewlett Packard, the company
yes,
Hewlett Packard.
yes, the company Hewlett Packard
Uh-huh.
and a small research group in Bonn. So they
Mhm.
both were the founders of swarm learning as a technique.
Mhm.
So they use this in just predicting a lot of diseases. So somehow COVID-19, tuberculosis, leukemia. But one of the drawback of the study that they did is they didn't use it on any image-based analysis. So it
Mhm.
was all text or tabular information for prediction of COVID-19, tuberculosis, or any other um, cases or diseases. But somehow, one drawback in this whole study was they didn't use any particular images or histopathology. And as I already told, my supervisor, his first Nature paper in 2016, in this paper, he showed that deep learning could directly predict mutations. So
Mm-hmm.
directly from the whole slide images, you could predict mutations in the Nature paper. So what idea we had is to combine both these studies, to use swarm learning as a technique and show that deep learning can predict mutation. And somehow what we wanted to show in our hypothesis is by having three different cohorts on three physical systems, and the performance of this on an external validation cohort should not drop when you have a centralized model. The swarm learning model should somehow perform on par with this centralized model. So this was the hypothesis, and this is what we tried to achieve in this whole study that we had.
Mm-hmm. Okay, so the main, like the main advantage that I see here, okay, performance wise, it's supposed to be the same as centralized, right? But
Yes.
because we're dealing with healthcare data, and there's a lot of regulations and it's very sensitive. So in the healthcare setup, we don't want to give away private information, of course. It's sensitive, it's health related, but there are also regulations. So in the US, it's going to be the HIPAA regulation. In the Europe, it's going to be GDPR, General Data Protection Regulation. And how does swarm learning align with that? Why is it better than the centralized? What are the advantages regarding treating patient information when we use swarm learning versus centralized learning?
Yes. So I will name two specific quotations or two specific parts in the GDPR article, that is 5.1c, which says principle of data minimization. So somehow when you use the data, the availability of data which is exposed has to be as minimum as possible. So somehow swarm learning kind of complies with this GDPR regulation, saying that we don't expose the patient data, and the complete data is not exposed to different centers. So we don't move data, we don't expose any patient IDs or patient information in the data. So somehow for this particular principle, it holds good. And there's another very important part in the article, which is 5.1p, which says principle of purpose of limitation. So somehow this is also very important to facilitate that we comply with this purpose of limitation, to somehow use the data only where it is useful. So somehow it is very important to use this data, just not exposing the whole image, but just by extracting information from it. So directly you cannot go back to the same image that is used, but only the features or only the weights and biases. So somehow we try to comply to this application also, but saying we don't have a white paper or a proof of document which says that there is also a study by Stephanie Rosello which also states some of the benefits of using federated learning, which is also a kind of distributed learning approach. So in this study, these two articles are mentioned, which say that the principle of data minimization and the purpose of limitation is fulfilled by federated learning, but there needs to be more research which shows shows concrete proof that this abides by all the GDPR regulation for data sharing.
So that's like a tricky thing to do, because in general, like deep learning and especially the weakly supervised, where you have the mutation status and the image, the like hype or the hope also was, oh, we don't really know which data is useful. Let's use like all the pixels and everything. And here GDPR is telling me only use the useful stuff. Don't use everything that you don't need, but we don't really know what we need. So I guess this is one way of dealing with this.
But I would like to give a small correction. GDPR says that only use what you need, which reveals the identity of the patient.
Okay, that's true.
So it should not be somehow revealing, say, date of birth, for example, or name of the patient. So this reveals a lot of information on patient identity, but these are the informations which should not be exposed to attacks or exposed to somehow information that anyone can get access to.
Okay. So tell me a little bit. So we already mentioned that since 2016, the group was working on predicting mutational status from the image, and your paper also talks about that. Let's talk a little bit about what your setup was and how many centers did you have? How did you show that the swarm learning is on par with centralized learning for what you were doing?
Yes. So, interestingly, what we wanted to do is do a prototype study, but somehow when we were using medical data, it was very important to use real cohorts. So, what we decided is to use cohorts from different country, which we had for analysis, but somehow we didn't do a real time swarm learning study. So, the cohorts from US were not based in US. They were in Germany in the lab, but in different physical systems. So this was somehow like a prototype study,
Mm-hmm.
but we put the data in physical systems separated, so there was no virtual machine. So in
Mm-hmm.
the previous study, in the swarm learning approach study, where the group from Bond showed that swarm learning works for COVID-19 prediction, it was all simulated on a single system. They had different virtual environments, and then they tried to predict some analysis on different kind of diseases. But what we wanted to do is show that this works on physical separate systems. So we put the data on 3 different systems for 3 different cohorts and try to analyze or predict mutations on this. So what we got out of that is 3 separate models. Those are the local models. Then
Mm-hmm.
we put on a separate system all 3 data together and then predicted the mutation. So this is the centralized model. So after all this analysis, we obtained a swarm learning model and then compared the swarm learning to the local models as well as the centralized model. Since we had all the data, we could compare it with the centralized model. But for the present studies that we are doing in a lot of other consortiums, we don't have access to all the data. That's why we
Mm-hmm.
cannot compare it to the centralized model. We can only compare it to the local models and say that it improves the performance when we compare it to the local model.
So you basically did a proof of concept. Okay, our method is not worse than what everybody else is doing, and now let's do it our way.
Yes, exactly.
Okay. And you said that the data for swarm learning, they were in different physical locations. I remember from the paper that you use a term metal core servers.
Yeah, bare metal servers.
Bare
So
metal
what-
servers. Bare metal
Yes.
servers.
Yes, this is a good point that you got. But somehow, what we meant by bare metal servers are these are physical commercial hardware. So like a desktop is a physical commercial hardware, which is not connected to a particular general server. So it is separated by not connecting it to any cohort or a group of systems, but it is independent of itself. It is connected to the internet with Bellon, and it's a physical system. So this is what we use for our studies is physical system, which is just connected to World Wide Web.
And this is something I learned that you don't have to buy them, right? This is a service like cloud computing. You can have it on virtual machines or in the cloud, or you can actually ask a service provider to have a dedicated bare metal server for you in case people would want to do this, like as a service or at scale and use providers for that.
Yes, definitely. So we have 2 approaches. Either you can have a cloud-based service, like a service with AWS or anything of that sort, or you could have a physical system, which is like a desktop in your center, which could be integrated with swarm learning and then somehow run the analysis. So these are the 2 different approaches that we can follow.
Which also gives the researchers and healthcare professionals options to be compliant. And because in different countries, the attitude or the regulations about cloud computing are different. I know that in Europe, it's required that, okay, if there is an audit, there needs to be a physical location required with where the data is processed. And I assume the bare metal server is something that can be located physically, and that's where the computation is happening. So let's go back to the concept of creating centralized slide repositories of whole slide images. And there are several different initiatives going on, multi-year initiatives. So the one that I'm very familiar with in Europe is Big Picture. This is a private public consortium in Europe. There are also initiatives going on in the US, like, for example, the Digital Diagnostics Foundation is working on aggregating images. So does it make sense to keep doing it, knowing that there are disadvantages regarding being compliant, and knowing that swarm performance is on par with centralized models? Tell me what you think about that.
Yes, definitely. I think it completely makes sense because these consortiums or these
So
projects
they
have
should
come up.
not stop. You're
No,
okay with them.
definitely. Yeah,
They can keep
definitely.
doing it. Okay.
Yes, I think it is pushing the field forward in a lot of
Mhm,
ways. So there are different applications of different approaches. So what
mhm,
we showed is a scenario where you actually cannot share data.
mhm,
So in big picture, a lot of consortiums or centers have agreed to share data, and they could somehow put all this data in a single center. But when
mhm,
it comes to a lot of different consortiums, because of the data regulations, they cannot share data. In this aspect, I think swarm learning or decentralized learning or distributed learning is the best way to approach. But if you have a consortium where all the partners agree to share data and the infrastructure in one single center, say a big center which is coordinating the whole consortium, has the facility to store all the data from all the centers, as well as has the capacity to process and train a model, everything on single site, then I think big consortiums like this really add a lot of value. But if
mhm.
there is a center which is not having the capacity to process all the data which is available, as well as to train a single model, then definitely swarm learning plays a very important role. So as you mentioned about big picture, I
Mhm.
was reading a little bit about this, and they also mentioned because of the scale and the data sets involved, and the GDPR regulations are sensitive about the data, the consortium is leveraging Okin. Okin is one of the very, very important central coordinator, which is handling the technical setup. They are leveraging federated learning techniques to, yeah,
Yes.
to enable the collaborative development of AI models. So one of the main reasons they are doing this is handling such a big amount of data, and training a single model on one single site becomes tedious when the number of sites increase, when the size of
Mhm,
data increases, and the compute power that is necessary, which increases. Why? Because in distributed learning, if you have 5 centers with a small amount of compute power, that is enough. But if you
mhm.
have all the data in a single place, then you'll need 5 times more powerful GPUs or powerful hardware to process and analyze this data.
So, question. For example, let's say there is an initiative going on with a lot of centralized data, and there is one partner that would like to benefit from that, would like to take part, but because of legal issues, they cannot share data. Would that be a use case to use them as like an additional partner in a swarm learning framework?
Exactly. That would be like the
Ah.
ideal case where we could use them as one of the partners and train a model which is shared with all the centralized model as well as them. So they will be a contributing partner for the swarm learning, and the other node will be this center with all the centralized, particularly whole slide images. So if they have some data with a specific mutation, then you
Mhm.
can train a single model with their data and the centralized data, and then get a model which is specifically trained for that particular mutation.
Okay, so if we have, and this is a known problem that we don't have the necessary diversity of data because some regional data or some specific ethnic populations they have there's not enough representation in those big data repositories. So basically, you could have a model or have, all the solutions that are training and check, okay, is it working on that specific patient population? If not, then do you then need to consolidate to have one model that does everything, or can you somehow have sub-models? How do you deal with that?
Yes, definitely. If there are different kind of mutations to train a swarm model, you would need each center to at least have specific information of that mutation. So if one center has no information for BRAF or MSI, then you cannot train a model from that data. So you can use that data maybe to pre-train or create a feature extractor, but somehow you cannot use the data to train a model which can predict MSI or BRAF, because this is very important even for a swarm model to have that specific mutation information in that cohort. If that information is never present, then you cannot use that data just for training.
So we basically need the same data pairs, like
Yes.
image plus label, whatever that is.
Exactly.
Okay. So going back to the specifics of your study on the mutation prediction from H&E, so what entities were you working with, and what were you predicting in that particular study? And did you extend the spectrum of what you're doing, or?
Yes, we were working on predicting microsatellite instability in colorectal cancer, as well as BRAF mutation in colorectal cancer. So these were the two important mutations that we wanted to predict, and which were available on the data, or which were available on the cohorts that we had. And then later, this was all with colorectal cancer. Later, we put a follow-up study, which is after this paper was published, we wanted to do the same on gastric cancer. We wanted to predict MSI on gastric cancer and also EBV on gastric cancer. So this was also a very highly cited paper, which was also informed about what do we need to which other use cases that we continued to go forward with the study. So these are some of the interesting use cases that we used in histopathology.
So another super important aspect in all these deep learning efforts is explainability. And I remember from the paper that you said, hey, the model flagged patches that were that you had you said that it's maybe has better explainability than other models, and the reasoning for that would be that, okay, the model took the information about mutation prediction from certain patches, and then pathologists looked at those patches and said, yes, this is compatible with the features, the histopathological features associated with the mutation. What if you work with tumors that don't have these kind of explainable features? Because not all of them have, right?
Yes, definitely. And I think that is a general question or challenge in the field, which even swarm learning cannot address, I believe, because somehow it is very important that these answerable features in the image is present, so that somehow the pathologist could look at these specific patches and say it is relevant to that mutation. So if there's nothing relevant to the mutation in the image, then that it is very important to see how do we predict these. Why? Because there's no information that is provided by the image to the viewer or even to the pathologist about this particular mutation.
But there are, you do not always visually know that there is some feature. I mean, colorectal cancer is a specific case where pathologists are describing different features. And, there are also other publications of, okay, let's quantify what we see and what we describe anyway, and see if it translates into any predictive properties of this image without even going into the mutational status, right? But what if we don't see that? Is there any? So what I'm getting at is how could we check this? Can we maybe take this particular, I don't know, do micro dissection of a histopathological slide of this patch that was marked as something, and then do a molecular test? Or any ideas on how we could approach that? Because that's probably like mm, there must be something to confirm. And I recently read a paper about using a commercially available software for marking EGFR mutations in lung cancer. And what they did, they basically took this piece of tissue and did a rapid PCR confirming that mutation. So, did you guys explore something like that, or do you have thoughts on that?
Yes, definitely. If we also have a possibility to get like PCR or any dissection on this specific tissue, then definitely it would be a very good proof for all the efforts and all the predictions that we do. And I think this is the direction the field has to go forward, is to have clear proof of all the analysis that we do. But unfortunately, we don't have access to this kind of data. So
Hmm.
somehow we don't have access to the slides that we could somehow do maybe
Yeah.
some other tests. So somehow there is this exact. So that's why what we want to do is show heat maps or show patches
Hmm.
which could visually say how it impacts this particular mutation, and then maybe a pathologist could go through this specific tiles or patches and then give us information on that. But we don't have access to this kind of data. That's why
Hmm.
I think, yeah, we cannot, I
Yeah, I
cannot
mean,
comment a
if
lot
you
on that.
only work on images, then the tissue is not in your data set.
Yes.
Okay, this is really, really insightful. So logistically, is the centralized approach easier or the swarm approach easier? If you
Logically, yeah,
logistically, like
logistic,
if you
yeah,
wanted to set up a partnership, uh, from how many partners it makes sense to use swarm. Let's say they don't want to share data. We assume they don't. Um, is it more difficult than trying to figure out how to share data and
no,
centralize? Or
definitely, I feel swarm learning is much easier in this aspect, because just to get a data sharing agreement, it takes months of efforts. To
Mhm,
set up swarm learning and to run an analysis, it just takes 1 or 2 weeks, depending on the uh, firewall and depending on the infrastructure that is specifically present on that center. Swarm learning is much easier and faster approach to train a model by actually not sharing data.
so what do you need to agree on then? Just say, hey, we would like to do a project together and our data is our and we don't tell you anything about it other than the labels for this model actually working on our data? Or like how do you initiate a partnership?
Yes, I think initiation of a partnership always um, has two side benefits. So somehow there is a center, for example, center X and center Y. Both of them have breast cancer histology slides, and they want to predict a very specific mutation for which they have some labels, or
Mhm,
but both of them don't have a big enough cohort to have a better performance
mhm,
or a low biased model. So what both agree on is, this is a use case, this is the model that we want to train, and we use both the centers. At the end, both the centers get the model, which you can use to validate on a new data set, and then somehow say this model is trained on our data as well as some other data for one specific application that you want to train.
mhm. And potentially you could actually, like if you had a method to rapidly confirm when the tissue comes in, when it's in a clinical setting, you could then um, do it and basically shorten
Yes.
the time to treatment, even if you don't have the option or don't want to aggregate. This is amazing. So what is the potential for commercializing models trained in this way? So commercializing models themselves, um, and also commercializing the method, or can you even commercialize the method like that? What are your thoughts on?
Yeah, presently we are using the software from the Hewlett Packard, which is
Mhm,
still in a community version. So they have
mhm,
announced that they'll keep it as a community software for some time now. So what you can just do is just this software is available or this platform is available for swarm learning. It is basically the intention is to commercialize the whole process of swarm learning. So
Okay.
somehow, yeah, this would, if you want to use this application, then you may need to pay the license to use the software, but presently it's still a community
So
version. So
let's train a lot of models now before.
yes,
Well, Hewlett Packard, thank you for making this available in the first place. And then let's train a lot of models.
yes, that's what we are trying to do is just not stick to histology. We have also tried a lot of project on radiology, video analysis, single cell. And so this can be integrated with any
Everything.
kind of data, which is, we work mostly on oncology, that is cancer research. So this can be established for any setup. And speaking about the point where you told about commercializing the model, definitely this is something which has to be compliant to a lot of regulations. So if you want to use a model on a commercial basis, like on patient data or to predict specific patient information, then there is a whole new regulation compliances that you have to, when you train a model, everything has to be standardized. So somehow this will take still a lot of effort to get a model standardized and commercialized, but this is the direction that we are going towards. So potentially we want to have a model which could be commercialized, and somehow any center can be able to access this by just putting their data on maybe a path, and then they get a prediction which is from our model, which is trained on all the data across the globe.
Okay. So it doesn't look too different from any other model commercialization, right? Because the platform, the swarm platform or swarm software is one thing. It's like a framework for training, but once it's trained, it's a tool that you can commercialize. And in order to commercialize it, it has to be compliant, like any other deep learning model for assisted diagnosis or for diagnostic purposes, right?
Exactly.
So now there is something known as the FAIR guiding principles for scientific data management. And this was also, this comes from a Nature paper, Scientific Data from 2016. And this FAIR acronym stands for findability, accessibility, interoperability, and reusability. And this is how the data should be for, science, healthcare, so that people can reuse, so that people don't have to do the same science twice. And I can imagine that, okay, in a centralized setting, you have it everywhere. Everything is in one place. You can find it. You can access it. And by the way, accessibility doesn't mean that it has to be open. There are different, gates, and it's gated data, but you can access it there. It's more or less interoperable and reusable. How can you assure that it's fair with swarm learning?
Yes, I think it is very difficult to be compliant with this guidelines of FAIR, because somehow it can be findable. So somehow we mention all the centers, all the like how is the data split between different centers. So findable definitely will. It is possible to let the user or let the guidelines see that from where this data was accessed and trained. But somehow accessible, we ourselves don't have accessibility to this data. So accessibility, even a different center, say center X and Y is using the data, even center Y will not have any access to the data from center X. So this is the main selling part of swarm learning. So this data won't be accessible, and it will be reusable if both the centers agree to train a model again, but it can be reusable. So that should not be a problem to be reusable, but both the centers should agree to retrain a model and then use the same prediction external validation cohort. So interpretability, definitely all the heat maps, all the explainable methods. So interpretation of our results are very, very fair. So that is possible, but making this accessible is something that is a little bit tricky.
I guess it's also like this definition of accessibility. If you can find it, then if people let you access it, you can access it, right? The thing is, okay, they might not let you access it. So I think it's uh, it's not specific to swarm learning. It's just enhanced by swarm learning because you don't aggregate. But in general, like, do you want the patient data, even in the limited way used for training of the models, to be accessible? And who is supposed to access it? Probably not every researcher that wants to do research on that, but they're findable and reusable if you can
Yes,
access.
if you're working on a data which is open source, and
Mhm.
then somehow a lot of the consortiums have initiative to publish or open source some section of the data, then I
Mhm.
think all the four can be very, very easily compliant. But somehow some consortiums cannot openly access or open source all the data. Then I think accessibility becomes one of the major concerns.
Thank you so much for explaining this. And it's a novel way of doing things, and I hope it's gonna get integrated into the ongoing initiatives. Are you guys going global with this? What are your plans? What would you like if you could have people do anything you want now after this episode? What um would you want to ask them to do? Those who want to use swarm learning, or in general, like, what's your mission with this?
Yes, I think the mission with us when we started swarm learning or using it for histopathology is to have each center, each histology center all over the world to just scan their slides and contribute to a model which is trained globally. All the centers across the world can train one single model for a particular mutation prediction,
Mhm.
or maybe a generalized model for multi-mutation prediction. So that's the final aim that we are working towards. But at the moment, we are taking smaller steps because this is the whole overview. Smaller steps is I would request all the viewers to read the papers, go through all the research that we are doing, and we provide a large variety of data modalities that we have already integrated with swarm learning. So if some center has some data or has a project in mind, which is similar to what we are doing in all the data availability, then they can always contact us, and then we can start up a project which can really be something very novel or something very important to the field. So contribution of each center here plays a very important role. And what other centers which provide data benefit is they get the same model that we get. So there's nothing that we take away. Everyone gets the same model which they use for, which is used to train their data, as well as the other centers which provide the data. So this is what I request: get in contact with us, and then
And
we are
scan your
looking.
slides. Please scan your slides.
Yes,
Because if we
definitely.
don't scan, we
Digitization is
cannot
the
do
way
it.
to go forward. Yeah.
Thank you so much for joining me. I hope I didn't confuse my digital pathology Trailblazer, but I'm going to link to the paper, link to my video of the paper where I kind of break it down in a slower pace. And thank you so much. And I hope you have a fantastic day.
Thank you so much for inviting me. It was a wonderful introduction to the study that we have done. And I would love to see some inquiries and, yeah, get back to you. And thank you so much for this wonderful opportunity.
Okay, and you made me dress up. So whoever have not seen it on YouTube, go and check out how we're dressed on YouTube. Thank you so much for staying till the end. This was a pretty complex subject, so I appreciate you even more. You are a true digital pathology trailblazer. So to understand exactly what we were talking about, there's gonna be the paper linked in the show notes, but also please watch this video where I break down Oliver's paper and see for yourself what amazing research they're doing. And I talk to you in the next episode.